So in this video, I'm going to run through the third practice test that I posted, and I'm also going to talk about question 14 that I didn't mention previously. So in question 14, it says that we've got 66 microliters of two different liquids put onto the same surface. And then it says half an hour later, the drops look like this. And so what's kind of happened here is it looks like we've got two drops with radically different surface area. One's kind of like, kind of tucked in on itself a lot more, and the other one is sort of like puffed out a lot more, right? So what's the difference between these two liquids? Well, I think that the best option here would be surface tension. You could also say intermolecular forces, but that's not two words. So I'm going to go with surface tension as being what's different between these two guys. All right, so now we're into practice test 2, and this first problem you're given a heating curve of substance S, and then you're given some written descriptions of substance Y and Z that are different from substance S in one way. So let's have a look at substance S and what's happening here. So it's showing what happens to the temperature of the substance as you add heat. At the bottom here, we've got solid. As we add heat, the temperature rises. In here, in that first flat region, melting is occurring. We're going from solid to liquid. That's going to be described by the enthalpy of fusion. And then in the second linearly increasing region, we have a liquid. And then eventually we get to the boiling point, and we're going to go from liquid to gas. And then once it's all evaporated, once we've given it the enthalpy of vaporization, then the gas will start heating up, and we have pure gas in that final linearly increasing region. Now, the important thing to realize is that the heat capacity in any of these regions here where we have a single phase, that's going to determine the slope of those areas. And then where we've got a phase change, it's going to be the enthalpy of fusion and the enthalpy of vaporization, and they kind of determine the length of that flat area, okay? And in particular, the longer that flat area is, the more heat that it takes to melt or evaporate your substance. Now, if we think about the heat capacity of, let's just say, the liquid here, if it takes more heat to raise the temperature of the liquid, then the slope will decrease. And if it takes less, so the temperature rises more quickly as we add heat, the slope will become more steep. So now let's go back to the question and see what we've got. So it says a pure substance, or a pure sample of substance S is put into an evacuated flask. The flask is then heated steadily and the temperature measured as time passes. The results are graphed below in the middle. And then it says identical experiments are now run on substance Y and Z. And substance Y is just like S, except that it has a higher heat capacity in the gaseous phase. So it's this part here that is the gas, and everything else is going to be the same. So the first parts of the curve, the first 1, 2, 3, 4 parts of the curve are going to be identical. And because it's got a higher heat capacity, that means it takes more heat to raise the temperature of the gas. The slope in the final part will be less. So what I picked out was a curve that was identical all the way through the first 4 parts of the curve, and then had a smaller slope in the gas phase there where the gas was being heated up. All right, and so, if you get lost with all of this, it labels what you're meant to be looking for. You're meant to be looking for a higher heat capacity in the gas phase. All right, so substance Z, it says, is just like S, except for it has a higher enthalpy of vaporization. So vaporization is occurring in here, and if it's a higher enthalpy of vaporization, we want it to be longer in that region. It takes more energy to vaporize the liquid. So everything else should be identical. The slope's in here, and the length of these first 3 bits should be the same. And then the slope of the final part there, when we have a gas, should be the same as the green curve. But this bit in here, it should be longer, right? Because we've got a greater enthalpy of vaporization. So that's why I chose the number 4 there in that case, all right? So you just got to kind of like think about it. Heat capacity is all about the slope. And then the enthalpy of vaporization or the enthalpy of fusion is all about the length of those flat regions. Okay, let's move on. Oh, a little bit of crystallography here. It says the distance between the red and green balls at the corners of this cube is 0.231 nanometers. So that's what we call the face diagonal between the red and the green. That's what we call the edge length. So L, right, equals 0.231. That's the edge length. And then it's going to ask, calculate the distance between the red and the blue balls. I was getting so excited I went ahead. So there's 2 things that you want to recognize is that the face diagonal, yeah, right, the face diagonal is equal to √2 times L times the edge length, okay? But the body diagonal, which is a little further, is equal to √3 times the edge length, okay? And so the body diagonal in this case would be like the distance between that red one and that one there, right through the middle of the unit cell. So there are 2 lengths that it's worth knowing the relationships for. So in this case, we're interested in the face diagonal, so it's simply √2 times 0.231 nanometers. There we go. All right. And this is going to be 3 significant figures, and so it ends up being 0.327 nanometers. And if you think about it, the diagonal of a square is always longer than the edge length. So keep that in mind. It should always be longer, and it is. And then the body diagonal of a cube, of course, should be even longer than the face diagonal, and it will be if you do the math correctly. So you don't have to work through from Pythagoras right from the beginning. That's like kind of a little bit of a waste of time. You can if you want. A squared plus b squared equals c squared, and then a squared in this case is going to be 0.231. You could do that if you wanted to. And you can just see that that's just going to end up being 2 times 0.231 squared equals c squared, and then taking the square root of both sides would just be the square root of 2 times 0.231 squared equals c, which is the same as √2 times 0.231 equals c, or you can just memorize that and be done with it. All right, so however you want to do it, it doesn't make any difference. You're going to arrive at the same thing, but there's no need to memorize the formula if you don't want to, or to use Pythagoras if you don't want to. All right, let's have a look. It looks like we've got a heating and a cooling curve here. Let's see what we've got. We've got 2 flat regions, so that's going to be solid going to a liquid. And then we've got another one up here that's going to be liquid going to a gas. Looks like we only get a little bit of the gas heating up. That's going to be pure liquid in there. That's going to be pure solid in there. So it says, what is the boiling point in degrees Celsius? Well, the boiling point is the temperature where a liquid starts becoming a gas, and that's going to be up here, isn't it? So we just want to make sure we're reading the scale correctly. 110, 120, 130. So that's 140, so that would be 135, and it's definitely degrees C. So I'm going to go with 135 degrees C. Then the next question is going to be reading a value of the x-axis. It says, what phase or physical state of X would you expect in the flask after 34 kilojoules of heat has been added? So let's have a look at the scale here. It looks like these are 2s, 2, 4, 6, 8, 10, yeah, and we want to add 34, so that's going to get us out to there. So there it is. So we go solid, solid to liquid, liquid, liquid to gas. And then it says check all that apply. So in here, we're turning the liquid into gas, but we're not 100% gas, so it's going to be liquid and gas. It's actually going to be a mixture. We're going to be in the process of evaporating it, right? We're going to be in the process of evaporating it. We're not quite there. We wouldn't be 100% gas until we were out by, looks like it's going to be about 39 kilojoules of heat's been added. Okay, so in this problem, it looks like we're looking at how temperature, pressure, enthalpy, and boiling point are all related. So it says use the observation in the first column to answer the question in the second column. So what we're looking at here is pressure or boiling point of a liquid at of two different liquids. So I think it's important to recognize how vapor pressure is related to enthalpy of vaporization and also temperature. So the vapor pressure above a liquid is determined by the Clausius-Clapeyron equation that basically says this. It says that the vapor pressure increases as the temperature increases. And in particular, it also says that the vapor pressure above a liquid increases as the enthalpy of a vaporization decreases. Now, in this equation here, I should point out that A and R are constants. And this is the single point form of the equation. We normally use the 2-point form. But the important thing to recognize was if you were to make a graph of pressure against absolute temperature, it would kind of look like this. As temperature goes up, pressure goes up, and the exact shape of it is going to be determined by the enthalpy of vaporization. So that's the general kind of thing that relates these three parameters of enthalpy of vaporization, pressure, and temperature. Now, the other little piece of information that you want to recognize is that the boiling point is simply the temperature at which the vapor pressure equals the external atmospheric pressure, which in the first observation here is going to be 1 atmosphere. So the pressure at the boiling point is just equal to whatever the external atmospheric pressure is. Okay, so and that's important, right? So it's just the temperature when the vapor pressure equals 1 atmosphere is what we call the normal boiling point. So it says at 1 atmosphere, substance A boils at 147 degrees and substance B boils at 160 degrees. So the boiling point of A is less than the boiling point of B. So then it says, which has a higher enthalpy of vaporization? So what does all of that mean? Well, when the vapor pressure is, so it just basically means this. It means that substance B must have a higher enthalpy of vaporization. It takes more energy to boil B. That's it, yeah. All right, so that's that's how that one's going to work out. So higher boiling point is equivalent to higher enthalpy of vaporization. Okay, then it says the enthalpy of vaporization of substance C is smaller than that of substance D. So it's really saying that it takes less energy to vaporize C than it does D. So then it asks which has the higher boiling point. And so what we're going to see here, the enthalpy of vaporization of C is smaller than that of D. So D must have the higher boiling point. So yeah, as one goes up, the other property goes up. Okay. Okay, so in this question, we're asked to consider substances S, Y, and Z. So they're going to give us the heating curve for substance S in the middle here in green. And you can see that we're heating up a solid to begin with. And then that solid melts and gets transformed into a liquid. And then we heat the liquid up. And then the liquid begins to boil and evaporate. And we begin converting it to a gas. And then finally, we're heating the gas up. So we have all 5 parts of the heating curve. For the flat areas, they're going to be determined, the length of those areas are going to be determined by the heat of fusion for melting and the heat of vaporization for evaporation. So how long those areas are going to be important. And then those areas where we're heating up either the solid, liquid, or the gas, that the slope of those guys is going to be determined. This is called the heat capacity. That's going to be is what's going to determine the size of the heat capacity, the slope. All right. So the steeper those linearly increasing regions are, that means the less energy is required to raise the temperature of the substance, and the less steep they are, then that means that we need more energy to raise the temperature of that substance. So let's have a look here. We have to select the curve that aligns with the description, and for Y, it says that it's just like S, except that it has a higher heat capacity in the solid state. So that means that the top 4 parts of the curve, right, are all going to be the same. So all of these bits are going to be the same, but it's just this bottom part where we're heating up the solid that is going to be different. And in this case, it says that we have a higher heat capacity. So that means that it takes more heat to raise the temperature by 1 degree Celsius. So that means that the slope is going to be a little less for that bottom region. So that's what I picked out. The curve that looks identical in every way as to S, except for the slope in the bottom there, was a little less, right? Okay. Now substance Z is exactly the same as S, except for it has a lower heat capacity in the gas phase. So that means that less energy inputted into the gas will raise the temperature more. So I picked the curve that was identical in the bottom 4 parts of the curve, and then that final part where we're heating up the gas, I wanted it to be steeper, because less energy in gives a greater rise in temperature. So you can see that when we're talking about a single phase, it's all about the slope of that linearly increasing region. And then when we're talking about a phase change, then it's how long those flat regions are. Okay. All right, so this looks like it's another crystallography problem. It says, select the sketch below that shows a portion of a crystal lattice with a body-centered cubic unit cell. So we have 3 cubic unit cells. We have simple cubic, where there is just an atom centered at the vertices of a cube. That's just called simple cubic, SC. Then we have face-centered cubic, where we have an atom at the corner, at each of the corners of the cube, but also in the middle of every face, of every single face. And I won't draw it out because it's complicated. That's called face-centered cubic. And then finally, we have the one that we're interested in here, which is body-centered cubic, which is just like simple cubic, except for there's an atom right in the very middle of the unit cell, as well as at each of the corners. So when we're looking for the body-centered cubic unit cell, we want it to have an atom at every corner We don't want any of the corners to be missing. And then we want one atom in the very middle, and we don't want anything else. We don't want any halfway along the edges. We don't want any at the centers of any of the faces, right? So it's got to be that guy there, number 7 in this case. Okay, there it is there. All right, next question. Okay, this looks like a crystallography question, probably a density one or a radius one. It says a certain metal, okay, crystallizes in a lattice described by a body-centered cubic unit cell. So BCC has a couple of properties. The first one is that you get 2 atoms for every BCC cell. And then we also have some relationships concerning the radius and the edge length. And so what we know is that the body diagonal, right, across the middle of the unit cell, that's going to be √3 times the edge length, which Alex gives us the lattice constant, is equal to 4 times the radius. So we have the radius, like, edge length relationship as well. Okay? Because the atoms in the BCC unit cell touch along the body diagonal. So here we go. It says the radius of R has been measured to be 138 picometers. Calculate the lattice constant. It's too easy. So it's the second of these properties, isn't it? So A is equal to 4R on √3. And A should be a smaller number than R because the body diagonal... The edge length should be a bigger number than R, right? So let's see what we get. So here we go. So 4 times 138 on second function √3, boom. And so it ends up being 319 picometers. And that makes sense, right? 319 picometers. It should be a bigger number than the radius. Okay, give your answer to the 3 significant figures. Make sure it has a correct symbol. We did everything in picometers. That looks great. All right. Now, sometimes you'll get asked questions about this for face-centered cubic. So for face-centered cubic, you just got to remember that you get 4 atoms per 1 cell. And then you need to remember that the radius edge length relationship is that it is √2 times the edge length equals 4R. Okay, so occasionally you'll get one on face-centered cubic. You won't really normally get one on simple cubic, but if you do get one on simple cubic, then simple cubic has 1 atom per cell, and then your radius / edge length relationship is that A is equal to 2 times your radius. So it's pretty easy. Okay. A small portion of a crystal lattice is shown below. What is the name of the unit cell? So it's either going to be simple cubic, face-centered cubic, or it's going to be body-centered cubic. So hopefully you can see that this one is very clearly simple cubic. You can put it as SC if you want. Okay. Select the sketch that shows a portion of a crystal lattice with a face-centered cubic unit cell. So the important thing here is that for face-centered cubic unit cell, every face has an atom at the corners of the unit cell and also one in the very center of the face, and that there aren't any atoms anywhere else. There's not one in the center of the unit cell, like right in the body center. There aren't any that are like halfway across, along an edge or anything like that. We should just have atoms at the corner, at every single corner, and then also in the center of every single face. So just take your time to select it. It shouldn't be a problem. Okay, what is this one? Okay, so a small portion of a crystal lattice is shown below. What is the name of the unit cell? Well, is it simple cubic? No, because simple cubic doesn't have an atom in the middle. Is it body-centered cubic, and yes, it is, right? So body-centered cubic has the abbreviation BCC, all lowercase if you want. And we know the only other one to check would be face-centered cubic, and it is not face-centered cubic. Okay? Because face-centered cubic has an atom in the center of each face. So it's got to be body-centered cubic. Body-centered cubic has an atom at the corners, at all of the corners, and also one in the very middle. Okay. In this problem, we have to read the description of a physical or chemical change and then decide if the change will be spontaneous or not. So the simplest way of determining spontaneity is by considering the Gibbs free energy change. So if the delta G for a process is less than 0, it's spontaneous. If a delta G for a process is greater than 0, it is non-spontaneous. And so that's kind of straightforward. Now, there's a little formula that will give us delta G. It is delta G equals delta H minus T delta S. Now, there is another way of thinking about spontaneity, which is that a spontaneous process always has a delta S universe being greater than 0, and delta S universe, of course, is equal to delta S of our system plus delta S of our surroundings. But more manageable is to consider the delta G. Most commonly, that's what we're going to do. And if you look in chapter 16, there's a little summary of all of the possible scenarios for enthalpy and entropy changes and how they're related to spontaneity. So this little table in here can kind of give you a heads up. I kind of just like reason through it, and you'll see me doing that in this problem. So in this first one here, it says, during an endothermic chemical reaction, a gas is consumed and a liquid produced. So what we want to know is what is the sign of all of the things that are in our formula for delta G, and then that'll help us decide if we know what the sign of delta G is. So delta G equals delta H minus T delta S. T delta S. Now T is always a positive number when it's expressed in Kelvin, and this says that this reaction was endothermic, which means that delta H is a positive number. And then what we're doing is a gas is getting turned into a liquid, which hopefully you can see is a delta S negative process. So now we have to think about how that's going to impact our sign of delta G. So delta H is a positive, and then we're going to subtract from that a positive for the temperature multiplied by a negative for the entropy change. So that's going to be a positive minus a negative. A positive number minus a negative number. And that's the same as a positive number plus a positive number, isn't it, right? So a positive number plus a positive number is always going to give you a positive number. So what that's saying is for this combination, delta G will be positive, and delta G positive means non-spontaneous. So we can tell in this case that this is not a spontaneous change. Now, if I go back to my little table, all right, I've got delta G positive and also delta S negative. So delta S negative, right, and delta H positive, it says delta G is positive at any temperature, process is non-spontaneous at any temperature, which is exactly what we decided. A negative and a positive, non-spontaneous. Okay, all right. Let's move on to the next one. I'm going to go through the same process. A solid precipitates from a solution, absorbing heat as it does so. So we're going to go from an aqueous solution to a solid. So hopefully you see that that is delta S negative. And then it says absorbing heat, which means it's an endothermic process, which is delta H positive. And remember, T is always greater than 0. So how does that affect our delta G? So delta G equals delta H minus T delta S. And we're saying that delta H is positive. We're going to be subtracting from that. a positive number for the T multiplied by a negative number for the delta S. So it's exactly the same as what we got before, a positive minus a negative, because a positive minus a negative gives you a negative. A positive minus a negative is the same as a positive plus a positive, and so this process will always give a delta G that is positive, so it is never spontaneous. Okay, and again we'll go back, have a look at our table. Delta H positive with delta S negative, it's always delta G positive at any temperature. It's always non-spontaneous at any temperature. Easy. All right. Next one. Let's do it again. A gas expands. So when something increases its volume, that is always delta S positive. And it does so without absorbing or releasing heat, which means that delta H equals 0, and our temperature is always a positive number. So let's see what we've got here. Delta G equals delta H minus T delta S. So this is going to be 0 minus a positive times by a positive. So 0 minus a positive. And so that's going to give me always a negative number, isn't it? Right? So delta G is always going to be 0 in this case. So yes, that will be spontaneous. Okay? So it's kind of dumb in a sense. Does a gas expand? Heck yeah. If you have a container full of gas and you take the lid off, it will spontaneously expand. Let's go back and have a look. I don't think it's going to be in the table because they probably don't have the case of delta H equals 0. They don't. So the table wouldn't have helped you out in that case. All right, but you know, you can figure it out just using the little formula there. All right, so you know, it doesn't matter however you do it, and whether you use the table or whether you use the formula, you're going to end up with the same result. All right, let's move on to question 12. Okay, it says the standard reaction free energy, delta G naught, equals 890 kilojoules for this reaction. Okay, so it's 1 mole of aluminum oxide plus 3 moles of hydrogen gives 2 moles of aluminum and 3 moles of water vapor. So when we're looking at delta G's and we've got these different kinds of things, there's a couple of things to remember. If you flip your reaction, you have to change sign of delta G. All right, and if you multiply your reaction, you guessed it, then multiply your delta G. So let's have a look at the first one. The first one we just plain old flipped it. So that just means we just got to change the sign on the delta G. In the second one, we didn't flip it. We just multiplied everything by a quarter. So that means I've just got to multiply my delta G by a quarter. Now I want it out to the ones because there's a decimal point there. So I want to give my answer, I want to round it off to the nearest kilojoule, which it said in the instructions anyway. Should have read it. So this ends up being 223. Okay, make sure you get the sign right. 223. Good. Now, in this last one, it's interesting. We flipped it and we multiplied by a half. So we have to do both those things. So to flip it, when I flip it, it becomes minus 890, and then I halve it, right? So it's going to end up being minus 445. Okay. All right. So that's the only tricky one, I guess, is where you do both of the operations, but it's not that difficult. Okay. Let's have a look at the next one. Oh, it looks very, very similar. Isn't it? Very similar. Yeah, looks very similar. So this guy here, spontaneous reaction. Oh, this is the thermite reaction. Very, very spontaneous. I know it's spontaneous because we've got a negative delta G. Okay, in the first case, it looks like we just multiplied everything by 3. So minus 835 times by 3. There we go. So that was minus 2505 kilojoules. In the second one, it looks like we flipped, so it becomes a positive, and then we multiplied by 2. Right? You can see that. You see the aluminum oxide is now on the left, but everything got multiplied by 2. So I changed the sign, and then I multiplied by 2. So 1670, and it needs a dot on the end for the sig figs to make that trailing 0 count. And then in the last one, it looks like we just flipped it. So it just becomes 835. We just changed the sign because all we did was flipped it. All right, there we go. So the first one, we just multiplied by 3. The second one, we flipped it and we multiplied by 2. And then in the final one, we just flipped it. So it's pretty straightforward once you realize the rules for dealing with this. Oh, this looks like we're actually going to be like calculating delta G's and stuff in this one. And I think the important thing to keep in mind here, and we're also going to have to comment on spontaneity. The important thing to keep in mind here is that enthalpies are normally given in like kilojoules, whereas entropies are normally given in joules, and temperature is your absolute temperature, so it always has to be in Kelvin. So we want to just kind of like keep all of that in mind. For spontaneity, we know that we need delta G to be negative. And then we just have the little formula that relates all of these things. Delta G equals delta H minus T delta S. So dimensional analysis just to make sure we don't get our kilojoules and joules confused. I should point out that we generally will express delta G's in kilojoules or kilojoules per mole. All right, looks like they want them here in and are using them in kilojoules. Okay, so let's see what we've got. All right, a chemical engineer is studying the 2 reactions shown in the table below. In each case, she fills a reaction vessel with some mixture of the reactants and products at a constant temperature of 131. There you go, there's your temperature, but it's not in Kelvin. So to get it to Kelvin, we've got to add 273.15 to it. So let's go ahead and do that right now. 131 plus 273.15. Here we go. So 404.15 Kelvin, and that's going to be the same for all of them. Then she measures the reaction enthalpy and the reaction entropy of the first reaction. Okay, so we want to be ultimately in kilojoules, it looks like, because we're going to be calculating delta G in kilojoules. So I'm going to leave my enthalpy is given to me in kilojoules, but I'm going to want to divide my entropy by 1,000 to get it into kilojoules per Kelvin, right? So I just divided that by 1,000. All right, so now what it asks me to do is that I should complete this table. So the first thing I've got to do is to go ahead and calculate delta G for the first one. So delta G is just going to be 1237 kilojoules minus 404.15 times 3, let's put that in the units in Kelvin. Just being super cautious because, you know, it's your final exam, right? Kilojoules per Kelvin. Now, the important thing to recognize is you can only add or subtract things that have exactly the same units. So you can, you can multiply things that have different units. You can multiply banana and an orange, but you can't add, bananas to oranges. So that's just the way the world works. So everything has to be in the same units when you're adding or subtracting. And that's why we did that conversion from joules per Kelvin kilojoules per Kelvin. Okay, so what I ended up getting for this, and you can see here the delta G is just going to be in kilojoules, was minus 6.1654 kilojoules. Now, it says round your answers to 0 decimal places. So this is just going to be 6 minus 6 kilojoules, right? To 0 decimal places. Minus 6 kilojoules. So that's a spontaneous process, right? Minus 6. And it is spontaneous. The reaction is written will be spontaneous. Now, remembering that we flip the sign of the delta G, we reverse the reaction. So if a reaction is spontaneous in one direction, it will be non-spontaneous in the other, and vice versa. So that's why it's asking about, is the reverse reaction spontaneous, right? Okay. Now, if the delta G equals 0, then you're at the balance point and it's going to be spontaneous in neither the forward nor the reverse direction. All right, T stays the same for both of these reactions, so we're just going to leave that be. And in this second one here, we're given delta H, 951 kilojoules. We're given delta G, 25 kilojoules. Remember, everything is to 0 decimal places. 25 kilojoules. And they're asking us for delta S, and you can see that they want it in joules per Kelvin. So when we originally calculate this, it's going to give it to us in kilojoules, you know, kilojoules kelvins, but then we'll convert. So delta G equals delta H minus T delta S. Always give the blank formula. Always give the blank formula so I know what the heck you're doing. It's highly recommended that you do your algebra first before putting your numbers in. So I know that you know what the heck is going on. All right, and now we're in business, aren't we? 25 kilojoules minus 951 kilojoules. What did I say? You have to be subtracting or adding exactly the same things, divided by minus 404.15 Kelvin. Now you can see that this is going to give me units of kilojoules per Kelvin, which we'll have to do a conversion on, won't we? So 25 minus 951 divide minus 404.15. So I end up with 2.2912. Now, I didn't write out all of the digits because I know I'm going to give this to 1 decimal place, right? So I get 10 to the 3 joules for every 1 kilojoule. And so that means that I've got 2291.2 joules per Kelvin. And we're going to round that off to 0 decimal places, 2291 joules per Kelvin. So that's a positive number for delta S, right? So this is the entropy is increasing. So let's just go and have a look and see if that makes sense. All right. So what do we got here? It's kind of hard to tell. I guess we got a bigger, floppier molecule here, right? And yeah, I mean, we have, if you look at this, 6. So we've got 9 atoms that are gas here, right? And we've got 2 atoms that are solid. And then over here, we've only got 6 atoms that are gas, and we've got 5 atoms that are solid. So definitely, like, more atoms have moved into the gas phase. So I would expect delta S positive. That's a reasonable, okay, that makes sense. All right. So what was our answer? With the correct units, it was 2,291 joules per Kelvin for the delta S. And then what is spontaneous? This reaction, the reverse reaction, or neither? Well, that reaction is not spontaneous because it is delta G positive. But if I flip the reaction, then the delta G would be negative 25. So that means that the reverse reaction is spontaneous. Okay, here we go. So this is the heat of fusion of that guy. So heat of fusion is to go from the solid to the liquid. Okay, and this is propane, going from the solid to the liquid, and it's not unsurprisingly, it's endothermic. You have to put heat in to make that process happen. Kilojoules, right? And then it says calculate the change in entropy when 9.6 grams of propane melts at minus 187.8. So what you have to recognize is that the change in entropy is equal to the heat transferred at constant pressure over the temperature at which the transfer occurs. And the temperature is always going to be the absolute temperature whenever we're doing thermodynamics. All right. So in this case, what happens? 3.5. We've got to do a little bit of, hang on, this is kilojoules per mole. It's not for a whole mole. It's only for 9.6 grams. Done it. We're going to have to get the Q, right? So Q is going to be 3.5 kilojoules for 1 mole. And then we're going to need the molar mass of this guy. So 3 times 12.01 plus 8 times 1.01 gives me 44.11 grams in a mole. And then we have upside down, but close. There we go. There's our heat that's going to be transferred, right? So our kilojoules per mole times by 1 on the molar mass times by the grams is going to give me the total heat transferred in kilojoules. So 3.5 divide 44.11 times 9.6. There we go. So it ends up being 0.76173 kilojoules. And we get 10 to the 3 joules for 1 kilojoule. So timesing that by 1,000, 761.73 joules. Okay, so that's our Q. So that's how much heat has to be transferred to melt this sample of propane. I guess we only need one last thing, which is the temperature, and we've got to turn it to absolute temperature. So minus 187.8 plus 273.15. Here we go, 85.35. 85.35 Kelvin. So we've got both of our bits there. Yeah, it doesn't ask for anything beyond that. It doesn't ask for particular units. So I'm just going to do it as joules per Kelvin because that's conventional units for entropy. Okay. So 761.73 joules on 85.35 Kelvin. Let's see what we get. 761.73 divide second function answer ends up being 8.9. Now it gives 2 sig figs joules Kelvin. So I'm pretty happy about that. Now we are melting this stuff, right? So yeah, we should have a positive entropy change. So I feel good about that. All right, there we go. All right, excellent work. Okay, that looks like that's it. So we're done with our practice test. And yeah, that's it.